Hello, and welcome to today's webinar. My name is Ben Weisenberger. I'm an application engineer with Allied PLM Solutions, and I'm joined today by Brandon Carter. In the next 30 minutes, we'll be discussing what makes Siemens PLM different from the competition. To begin with, we're going to talk about how Siemens PLM is a complete solution from design to manufacturing and everything in between. We'll then talk about some key Siemens technologies that help us stand out from the rest, including Synchronous technology, generative design, and convergent modeling. And finally, we'll finish up by talking about the support and training available to you through both Allied PLM and Siemens PLM to help keep you up to date with all of the latest technology. So with that, let's go ahead and get started. So again, to begin with, we're going to talk about how Siemens is our complete integrated solutions. And what we want to start with is the Siemens PLM suite of products. They can help us take your ideas from cradle to grave and anything and everything in between. You can easily take your ideas and concepts and create working, detailed designs of them. Those designs can then be analyzed using simulation to validate real-world functionality and performance. After that validation, the tooling and fixtures can quickly and easily be designed around the finished product. Those designs can then be sent straight to CAM programming and manufactured in the real world to be delivered to your customers. Simultaneously, during design and manufacturing, all designs and documents can easily be maintained and any changes tracked through the world's most widely used PLM software, Teamcenter. NX offers the industry's broadest suite of integrated, fully associative CAD, CAM, and CAE applications. NX touches the full range of development processes in product design, manufacturing, and simulation, allowing companies to encourage the use of best practices by capturing and reusing product and process knowledge. Solid Edge is a portfolio of software tools that addresses all aspects of the product development process: 3D design, simulation, manufacturing, design management, and more, thanks to a growing ecosystem of apps. Solid Edge combines the speed and simplicity of direct modeling with the flexibility and control of parametric design, made possible with Synchronous technology. And that leads us into Synchronous technology and how it's different. So the most common type of CAD system available in the marketplace uses what's called history-based modeling because it has a couple great benefits, such as being dimension-driven. Both Solid Edge and NX have been history-based modelers, and they continue to provide this method. However, we've worked this way for so long that we've learned to kind of ignore the not-so-good things, such as having to pre-plan the model. So looking for a better way to work, we can turn to direct modeling. This has some great benefits, such as direct interaction with the model, but there are downsides to this method as well, such as being featureless, so it's not very organized sometimes. So how about taking the best of both worlds, but leaving out the downsides? So this is why Siemens created Synchronous technology, with unique items such as 3D driving dimensions, space relationships, to really synchronize these worlds. So in fact, the technology is so unique to Siemens that there are actually 8 patents granted, with a further 23 pending. Improvements to Synchronous design intent management enables us to focus on our designs and less on the tool, which results in an accelerated modeling process and shorter time to market. In the history-based CAD world, it's often common to refer to imported data as dumb geometry because the metadata necessary to drive the history-based features is never transmitted along with the geometry. This is true whether we transfer the data between 2 entirely different CAD programs or sometimes between different versions of the same program. You'll lose all of your intelligence or design intent in a data import, and I'm sure we've all dealt with that before. But with Synchronous technology, the design intent comes from the geometry itself, not from the metadata stored with the geometry. So this allows us to work seamlessly with the data from any source. For instance, if there are parallel faces, the chances that those are parallel by accident are probably very low. So the software assumes that this is intentional and retains that relationship as our design intent. Synchronous technology can even recognize things like patterns or holes on imported parts and can create those as editable synchronous features. And that leads us into our first demo. So we're going to take a look at synchronous technology on how that works, and we're going to take a look at it to begin with inside of Solid Edge. What we're going to do is we're going to actually import a part file and start to do synchronous edits to it. So I'm going to open up a Parasolid file. I'm going to import that into just an ISO part template. So here's the geometry we're going to work with, and we're going to start by focusing on the cutout here in the middle. As we select a face, you'll notice that we get a heads-up display of our default design intent relationships. So this gives us a clear picture of what types of geometric relationships can be detected automatically based on our selection. As we begin to drag that selected face towards the middle section, notice how the coplanar faces are automatically detected. In our case, we don't want them to maintain that relationship, so we simply uncheck that box in the design intent panel, and we don't have to move the coplanar faces anymore. So efficient management of our design intent allows us to focus on our design and not necessarily on the tool. Next, we're going to add a couple of new features to our design. Synchronous technology, it makes our modeling easier and faster by simply selecting regions of sketches to push or pull to create features in our part. We can also come in and add a couple other features. So this just helps facilitate faster geometry creation. So again, as we perform another synchronous edit here, and this time we're going to do a rotation, you'll notice the default symmetric design intent that is found and maintained automatically. In this particular area over on the side, you'll notice that there's another face that is parallel and the step above the selected face. So inside of Solid Edge at any time we can go into the Advanced Design Intent panel where we can enable other relationships that are not turned on by default, as well as enable other advanced features inside of the design intent. More recently, there have been some other improvements added to help enable dragging features that cross over stepped faces to help them react as a separate set of geometry. So you'll notice as I start to drag this, it pulls the feature out away from the rest of the geometry, and it now does not automatically extend the faces. But of course that option's optional, so we can always go back in and have control over how it reacts to the rest of the geometry in the quick bar options. Occasionally new design intent rules are created to help maintain our design intent of our models. One of the new design intent rules for Solid Edge is the offset relationship. You'll notice how it maintains the offset thickness between the top and bottom faces of the cutout. If we toggle this option off, you notice we only move the top face of the cutout. Next, we're going to create a line. And we're going to create this line by midpoint. By creating the line by midpoint, we can use it to automatically build symmetry into our design intent. So in this case, by creating that as a construction line about the center of the part, it'll ensure that any geometry we attach to the endpoints of that line will be symmetric from one side of the part to the other. So these two holes that we place at the endpoints will now be symmetric to each other. The sketch is simply, again, just used as reference to add design intent of the symmetry there. As we start to move one of these upper holes, you'll notice we pick up both symmetry and align holes. not only can you go to the design intent panel and uncheck one of the boxes, we can actually toggle on and off the design intent rules using keyboard shortcuts. In this case, we're going to toggle the keyboard shortcut for aligned holes by pressing A on the keyboard. That'll keep the adjacent holes stationary and allow us to just move our symmetric holes. Our models can also be driven using PMI dimensions, or driving 3D dimensions. So I'm going to attach a dimension between our holes here on the side of the part. I can then symmetrically drive those two holes away from each other, and again, design intent automatically picks up symmetry across the model. We can toggle off things like concentric holes, which will remove the concentricity between the holes and the rounds on the edge of the part, or we can toggle that back on and make a change to our model. And finally, if all of the geometry that we wish to modify is in one select set, what we can actually do is disable all of the design intent rules by unchecking design intent at the top of the design intent window, or by pressing U on the keyboard. This ensures that only the geometry that we have selected will get modified. So in this case, we'll rotate that geometry 45 degrees. So solid edge with synchronous technology, but also similarly NX with synchronous technology, allows you to design the way that you want to. Flexible modeling incorporating synchronous technology frees you to intuitively produce realistic, accurate designs faster, reducing time to market and product development costs. So now I'll go ahead and hand the presentation over to Brandon Carter to discuss generative design and how that makes Siemens PLM different.
All right, thanks, Ben. Hello, everyone. As Ben mentioned, my name is Brandon Carter. I'm also an application engineer with Alleviate PLM Solutions. I want to thank everyone for joining us today. The next technology we want to talk about is introducing generative design. So as designers, if you think about your CAD system today, we design multiple ways. You know, maybe it's a bottom-up approach where we've already modeled the parts and then we're going to put them together in assembly. You know, we also maybe model with the top-down approach where we're modeling geometry or editing parts in the context of assembly. Maybe we do that method so we can reference background components, you know, for fit, function, etc. As we model these parts, our focus is typically to get a solid. If you think about your individual component, you know, we're trying to maintain solids, model with solids. Our result needs to be a solid body. Once we get the main design intent in our designs and the features the way we want them, we might come back through and try to manually optimize the design. You know, maybe we, you know, rethink certain features, you know, try it a different way, maybe add more pockets or shell commands to reduce weight and material, depending on what our manufacturing process is. So generative design, which is what we're talking about here, and sometimes it's referred to as topology optimization, does this for us. So what this optimization does is it helps us meet specific strength, material goals, all while minimizing material costs and or weight. This can give us an organic shape, as you see here on the slide, what's here in the blue circle. You know, different iterations of this, you notice how it gets more of an organic shape. Excuse me. So you know, this shape, it also would depend on what our manufacturing process is, and a lot of times we can take advantage of additive manufacturing, which we'll talk about a little bit later. So Siemens, we now have this technology. The basic workflow is very similar to that of a simulation study or an FEA setup. FEA, I mean finite element analysis. Basically what we do is we apply a load or a constraint, or in a constraint. The constraint can be location parts. For example, this lower left-hand screenshot, we're designing this part in the context of the assembly. So our constraints can be, you know, where is this part at? Where is it constrained in the assembly, and so forth. In the middle screenshot, we can model keep-out areas. So these are just going to be kind of solid bodies or voids where we don't want any material. We want kind of cutouts to be. You know, maybe an example of having that void is for a harness to run through there. maybe there's electrical components, maybe there's potential interferences for linkages, depending on how that assembly is going to move. Basically wherever there needs to be an empty area. And then we push go. The software will go through iterations and provide a model. So generally speaking, if we step back a little bit, some of the softwares in this area of topology optimization, they provide parts, but they're not completely usable. Sometimes they'll have weird lumps or shapes to them. And with those systems, the designer still has to go back and use the shape as reference, model around that shape, just kind of have that as a reference for what an optimized shape would be, and then still design manually. What makes this state of the art is, that the fact that we can use this geometry. Okay, so this kind of leads us into the discussion of additive manufacturing, and there at the end I'll tie all this together, so just bear with me. Additive manufacturing, this has been growing and becoming more mainstream. It's not just for the weekend hobbyist anymore. I think this is a really exciting topic in manufacturing with the advancements in using more metallic type materials. Additive manufacturing is becoming more looked at, or being looked at more and more. Companies are 3D printing parts in-house. They can also tap into a network of companies that provide 3D printing as services. This can help companies, optimize cost and delivery because there's that service out there. If you're not familiar with additive manufacturing or 3D printing, a common file format for that is STL. Okay, so with additive manufacturing, you can easily create prototypes. So a lot of customers will, they'll start, introducing or start using additive manufacturing just as prototypes, but as mentioned on the previous slide, even final products are being defined or being created, manufactured in that environment. So with that being said, let's look at some of the tools that have been added for 3D printing and additive manufacturing. The first screenshot you'll see here is inside of NX, there have been some additive manufacturing templates added. So what happens is you start this template as like a manufacturing idea, and then you can add your part that you want to print into this as like a little assembly, and you can add support structures. You can slices can be viewed, just like you would build layers inside of a 3D print. And the part can be printed directly from this environment using kind of a, I say, post-processor type format or workflow. Also, straight from inside the CAD system, you can do a file 3D print, similar to what you've done print in the past. When you do this file 3D print, it takes advantage of the Windows 3D Builder. Also, there are tools to help us validate the requirements. Basically answer the question, the part that I'm trying to design, is it valid for us to 3D print? So with that, let's take a look at some of these tools. All right, here on the screen, this is a little business card holder. Ben and myself, we actually use this as one of the projects in our training classes. We have a tabletop, desktop 3D printer, and we print these out, and the students can take them home. But what we want to do is look at this design and validate that it's going to work for our requirements. So over here on the Analysis tab, you see that there's tools added for design validation specifically for additive manufacturing. So the first thing we want to look at is wall thickness. So what this is going to do is we can specify what our minimum thickness needs to be, and then the software will go out and check and say, hey, where would be areas that this is too thick for that minimum thickness requirement? If I change this value maybe down to 0.1 and recalculate, you'll see that there may be some different faces change, but I'm still thinner on the geometry than this 0.1. One thing you'll notice down here at the feet in certain areas it's green, which means it's above minimum thickness. I can also turn on an option to de-emphasize the area so that you don't even see that area and only focus on what's red. So in a nutshell, what we're doing is looking at our geometry on the fly and saying, hey, how does this stack up next to that minimum thickness requirement for printing? Another thing we can do is look at overhang angle. The overhang angle is basically, is there going to be any steep angles where you have to worry about fall off of the 3D print? You know, is the structure going to be you know, messed up? Is the layers going to start to overlap or fall off? But in this case, I have a default value of 45, so everything is green. If I change this down to 10 degrees, notice the feedback I get in red, that's where the angle is 10 degrees and what that maximum overhang would be. The reason why the 10 degrees shows up here is this part's been drafted with 10 degrees, which makes sense why that would show up. And then finally, there's printable volume. It sounds very simple, but this is very handy as well. We can enter what our print volume for our 3D printer is by length, width, and height. Here we have default values of 8 by 8 by 8. And obviously with a quick check, you see that that part can be printed in this particular volume. Here inside of NX, this particular check goes through the Checkmate user interface, so you can get more information following the graphical tabs here. And specifically, whenever I look at that check, it says the part build size is length of a little over 4, width of a little over 1, and height of 1.45. So I get that information just by running that check, even without necessarily measuring the extremes of the part. So the point there is, if we're going to be serious about designing parts for 3D printing, it's nice to have some tools to validate that that fits within our requirements. All right, so the next thing we want to talk about, the next technology that is convergent modeling. So we just discussed what we call easy for me to say, generative design. We also talked about our design here in the center where we're used to doing solid bodies. Then we talked about on the back end, you know, sending this to 3D print, being able to manufacture this. One thing we have not talked about yet is this reverse engineering. Reverse engineering typically comes from the idea of scanning something, right? We have some kind of scan, we scan a part that's existing, and then, you know, we read that in as a point cloud or an STL file. So at this point, we have that geometry as STL. How do we make that usable for our design to be a solid body, in lack of a better term? If you're not familiar with STL geometry, when you bring that into a CAD system, it's a series of triangles or what we call facets. So it's not really usable geometry. You can't edit it, you can't add to it, you can't subtract, can't add other features to it. So the reverse engineering process is to build surfaces over top of that facet geometry, sew those surfaces together, therefore giving you a solid body which matches what we already have in our design. One thing to mention with the generative design we talked about earlier is this is what we consider to be a mesh solid as well, which is facet. We just talked about scanning in through STL, that being a facet or what we're going to call a mesh solid. And then on the back end, spitting that out to a mesh solid in STL for 3D printing. So you can see if we're used to working with solids and having these mesh solids being read into our assembly or being tried to use into our project, our assembly, you know, how do we get that to work without doing reverse engineering? So what happens is we have the concept of convergent modeling, which is the missing link. And convergent modeling is the ability to really just use that STL data. Be able to use that STL data as tool shapes for subtraction, for Boolean, to be able to maybe even trim that STL file, but basically just use it without the need, or at least a reduced need, for that reverse engineering process. All right, so let's take a look at a couple examples of convergent modeling. All right, let me come over here to another part. Actually, this is going to be just a blank file. And the first step I'm going to do is just import an STL file. So I'm going to import this STL file called the skull. And like I said, if you've ever imported an STL file before, you know it's triangles. It's that facet geometry I was talking about. Now what you'll notice here inside of NX is the ability to make this a convergent body. So as this comes in, yes, it still looks like an STL file, depending on the resolution of how that was scanned and the resolution of the STL file. It could look a little jagged like it does here, but the reality is, look how this is a convergent body, right? What that means is we can use it. So our design intent here is to build a cranial implant, or this little patch that goes across or on the side of the skull. So what I'm going to start off with is just using, general CAD methods. I'm just creating a sketch here on the plane. Drag this around and kind of get the shape I want. So right now we have a sketch there on the center plane, and really what we're talking about with convergent modeling is the ability to come in here and just start referencing that. Notice with the divide face command, I can actually reference that STL file, that STL data, and I can go ahead and divide that surface using this divide face and project those curves normal over to that face. What that allows me to do is then extrude a shape. So once again, the point is I didn't have to go in and build surfaces, reverse engineer. I was able to just reference that STL data to create my new solid. I'm going to go ahead and change this to another color just to help highlight the different solid here. I'll go ahead and just pick a green color or something. But you'll see I have my new solid referencing that convergent geometry, and as I mentioned prior, there was no need to reverse engineer that first. Also, we're able to actually treat this solid body, meaning we can add features to it. So what we're going to do here is just come in here to the center plane again, build some construction geometry. Maybe I need to cut off the bottom of the skull. I'm just going to do a rectangle by 2 points here. Build some other construction geometry for the shape that I need. Do a quick trim. So as I start to extrude this, I'm going to extrude this symmetrically. And notice on the fly, I can subtract that shape away from the STL data. Once again, there wasn't a need to reverse engineer that. I have another example that I want to look at, staying with the medical theme. This would be for any industry, but just looking at the medical theme, medical industry for right now. Here's a scan of a knee. Also inside of here, we have a solid body modeled, which is going to be this plate, this bracket to hold the knee together for surgery. Now, right now, you'll notice that the STL data is interfering with that bracket, and to get a nice fit, it'd be nice to be able to subtract that knee away. So once again, without reverse engineering, I can come in there and subtract that knee away, and I'll get that result. Notice we could just go directly to the Boolean operation and use that as a tool body. So convergent modeling is really being that glue that's going to allow us to use the generative design, use scans, and minimize the need for reverse engineering. So to recap and put all this together, we looked at a few different technologies here. No other solution has synchronous technology, the convergent modeling. We talked about tools for additive manufacturing as well as the generative design. Siemens PLM offers completely integrated solutions, whether that's from design in CAD, through simulation with CAE, all the way through CAM and manufacturing. And then all data can be managed inside a team center. As Ben mentioned earlier, this covers the product from cradle to grave, from concept through manufacturing as well as managing the data. So a little more about Siemens PLM. You may recognize some of the logos on here, but just as important are the mid-sized to smaller companies. The Siemens PLM software suite makes it easy to grow your software solutions as your company grows because it's an integrated platform. So we spent the last, 20, 30 minutes or so discussing the Siemens technologies, specifically generative design, synchronous technology, and convergent modeling. But to point out, Siemens also owns and develops the Parasolid kernel, as well as the D-Cube solver. If you're not familiar with the Parasolid kernel, it's the core modeling engine found in Solid Edge and NX, but also other software platforms lease the kernel from Siemens. They also lease the D-Cube solver, which is a 2D sketch solver. So who is alleviate PLM? We are a partner of Siemens. We have 35 years as a partner. We have customers who stay with us for technical support. We handle technical support in which we have a 98% satisfaction rate, as you see here. And one thing about our business model that's a little different than other companies like us, we staff differently. Our focus is on support, as I mentioned. We have a 3-to-1 staffing model, engineers to sales. Some companies staff more salespeople compared to engineers. So we have a 3-to-1 engineering to sales ratio. So through superior support, flexible training, and our training content, we focus on the customer. You may have watched some of our videos called Lunch Bites on our website and YouTube channel. They're pretty popular. If you have not, you might want to check those out. That gives you an example of what our content is. Also, there's some more details on Synchronous technology in some of those videos, as well as Convergent modeling. So before we sign off today, I just wanted to mention one last thing. Siemens is not only a recognizable name for making products, but Siemens PLM Software brings technology to the forefront. Siemens Industries use these technologies, right? So not only are they, Siemens Global not only makes products, but Siemens PLM, provides these technologies and they get used. Synchronous technology, generative design, the tools for additive manufacturing, as well as convergent modeling are innovative technologies that are going to help you prevent rework and bring your products to market faster. So with that, Ben and I thank you for your time. If you have any questions, you see our email addresses there. It's Brandon Carter at alliedplm.com or Ben Weisenberger at alliedplm.com. Please reach out to us and we'd be happy to answer those. And we thank you for your time and have a great day.